Thank you, whoever said that. Okay, we're back in business. Okay, sorry for the delay. Let's get on with it. So here's an idea that's going to come up with series solutions that are for more complicated problems. We're still in the linear algebra part of the series solution thing. So we're still talking about eigenanalysis. And I'm going to talk about symmetrization. So if you've got a matrix that's not symmetric, well, and of course, pick a matrix at random. I mean, what does that random mean? But anyway, it won't be symmetric. Then in general, eigenvalues can be complex, and this nice orthogonality property of eigen vectors is not there. But some are, I'll say, close to being symmetric in the following way. So if you've got a matrix E, okay, and this matrix E is going to be symmetric. Okay, remember, if it's symmetric, then it has real eigenvalues. Remember, you saw this last lecture, I often confuse eigenvalues and eigenvectors. Okay, so it has real eigenvalues. Then I'm going to look at a reduced class where these ones have all positive eigenvalues. Okay, and that makes this a SPD, symmetric positive definite. Matrix, okay? And symmetric positive definite matrices have even more structure than just symmetric ones. By the way, you can talk about positive definite matrices that aren't symmetric, but the criteria then gets a little bit more complicated to describe them. Here it's easy, it's just they got to have positive eigenvalues. And one of the things that I'm going to use is that this E can define a weighted inner product. So I've got the regular inner product. Okay, how do you get the regular inner product, right? You just take these are n component vectors here, right? You take the corresponding components, multiply them together, add them all up, right? That gives you the inner product or dot product. Now I'm going to make a new inner product. So this is going to be a different one in which I take U and then I take the inner product with E. So this E, this makes it a new inner product. And this is showing over here, this is showing how you actually get it in terms of the old inner product. And I can say without proof UVE has all the properties of a inner product. In particular, if I take the inner product of U with U, that's greater than or equal to 0, and this would be like the norm of E of U in this thing squared, right? And only 0 if U is the 0 vector. Okay, and as a kind of an easy example, if I've got a diagonal matrix with positive entries, so there it is, zeros everywhere except on the diagonal, and these are positive entries. Then this is just like a weighted inner product and norm, right? If I look at the norm that's going to come from this is just the sum of the squares of the UI entries, but weighted by these positive weights. And you may have seen kind of weighted things before. I'm thinking of the physics students, but this could have come up in others for other students as well, maybe in statistics courses. You're doing like least squares fitting. If you have some of your measurements which you trust more than others, then you weight the residual on those larger than the other ones. So this is that's a kind of natural way where these kind of weighted inner products can come. And the diagonal one is the easy one. And it's going to be the diagonal idea that's going to come up when we talk about a series solution. Okay, so now I've got this matrix A that is not symmetric. And if I can find an E that's SPD, if this can be made symmetric for a given SPD matrix E, then the matrix A is called symmetrizable. Okay, and what happens there? Basically, the matrix is just symmetric in the E inner product. Remember, we got away from the idea of thinking of symmetry as being like the coordinates were the same, ij and ji, and we got the idea that it was that you could take the matrix from one side of an inner product and put it on another, and so we can do that with this matrix now, as long as we don't use the regular inner product, but the other one. Okay, so let's see how that goes. So I'm going to take this thing in the E inner product and show that I can move A over to the other side, so it's symmetric in that new inner product. So remember, this is the same thing as U inner product with E times the right-hand side in the usual inner product, so without the E. This is symmetric, so I can move it over there. The whole thing is symmetric. So I'm going to have E times A times UV in the usual inner product. I'll put a little dot here to indicate it's not the new inner product, it's the old one. This one is symmetric, so I can move it to the other side. right? And this is just this is just A times U inner product with V in the E inner product. So if I go from, okay, let's get another color. I like this kind of light blue one. If I go from here to here, this is showing that A is symmetric in this inner product, the E inner product. Okay, and it's a little bit subtle, but now we can use the same argument we used before to show that the eigen values have to be real. And the eigen, okay, help me out here, vectors are going to be orthogonal, but E-orthogonal. So that means if you've got an eigenvector corresponding to different, two eigenvectors corresponding to different eigenvalues, then if I look in the E inner product, they'll be orthogonal. That seems like maybe we should have an example where you see how this works, okay? And I'm showing you this because this is an idea that comes up with series solutions for these boundary value problems. And the series solutions are also going to be useful when we start talking about parabolic equations where we've got some time dependence. So let me give an example. I had to play around a little bit to get an example where the numbers were good. Okay, so there's my matrix. Oh, sorry, I played around with the numbers. Oh, there's a question coming. Yeah, so in this thing up here, this is, we're assuming that this is symmetric. So the matrix A wasn't symmetric, but we managed to find this E so that E times A was symmetric, and then all these properties follow. Remember, like not every matrix has real eigenvalues or orthogonal eigenvectors in any sense. So this is an extension of the idea of symmetric matrices, but it's just a bigger class. It's not all matrices that this happens for. Okay, so I'm going to change my matrix. This is the one I found where the numbers worked out kind of well. MATLAB helped me out a little bit as I was exploring for an example. So let's look at this guy. This is not symmetric. Right, but it's 2 by 2, right? So it's easy to sort of see how it goes. Basically, what I want to do is I want to multiply this row by a half, right? And if I could do that, then the matrix would be symmetric because I'd have the 1 and the 1 here. And if you were allowed to left multiply by matrices and you just want to change one row, that's a diagonal multiplication. So here's my E matrix. It's going to be one of these diagonal matrices with positive entries, so I know it's symmetric and positive definite, right? And if I take that matrix times this one that isn't symmetric, then I get minus 3/2, 1, 1, minus 1/2, and that is symmetric. So I've made it symmetric. Okay, and so now I know the eigenvectors or the eigenvalues will be real. And the eigenvectors, there'll be 2 eigenvectors. These ones will be E orthogonal. orthogonal. And what does that mean, right? So if I've got my V1 vector and it's got components V11 and V12, right? And the same thing with 2, that would mean that if I take a V1 E inner product with V2, that should be 1/2 times V11 V21. Oh, I got a question. Oh, here's an excellent question. I don't know the answer. The question is, if you have a matrix with all real eigenvalues, does that mean it is symmetrizable? Okay. Okay. No, actually, I can answer that now that I think about it. No, because remember, one of the other things that come from the symmetry is that you have the matrix can't be deficient. It means you have a full set of eigenvectors, right? And you can have a matrix with real eigenvalues that only has one eigenvector. So this would not be symmetrizable. Only one eigenvector, right? That's the other nice thing that comes from symmetric matrices is you know that you never have that case where you've got repeated eigenvalues, but less eigenvectors than the number of repetitions of eigenvalues. Okay, so the way that these things should be orthogonal is an inner product, but with this half for the first components. This will be a 0, and I'll show you what they are so we can check. Again, I played around in MATLAB to find this example with numbers that turned out sort of nice. So you can check that these are the eigenvalues and eigenvectors. I didn't normalize the eigenvectors. Of course, when you're doing MATLAB, then you have to like interpret the eigenvectors to get these nice values. And you can see here that if I take the inner product of V1 with V2, it's not 0. But if I take the inner product of V1 with V2 in the E inner product, it is 0, right? You can actually just do this explicitly, right? It's -2, but multiplied by 1/2 plus 1 gives you 0. Okay, so this is the warm-up for series solutions. So let's do the series solutions. So we're going to do the series solutions to boundary value problems. And I'm going to call this part 1, because we're going to come back to this after we take an aside and look at Green's functions, which are old news for some people. The top person on my list there.
Why does everyone pick on me?
Because you're at the top. I don't know if it's, I actually know from other Zoom meetings that everyone sees a different order, right? So you can't talk about the person in the upper left. Okay, there's some chatting coming up. Is that okay? Maricela will let me know if I need to do something about that chat. Okay, so let's look at this problem. And remember, when I talk about a boundary value problem, it's not just the differential equation part, it's the boundary conditions as well, if I want to talk about the problem. And so it's linear. I'm going to encode that whole problem in this notation. It's L times U is equal to F. So this includes the boundary conditions. Right? And in this way, it kind of looks like a matrix problem. I'm going to tell you, so details to follow. But I'm going to say L is symmetric. Now you know if I'm going to tell you something is symmetric, I have to tell you about the inner product that it's symmetric in, right? Okay, so I'll get to that. It has real eigenvalues. And has an orthonormal basis of eigenvectors. Again, if I'm going to talk about orthogonality, I have to tell you the inner product. And if I'm going to talk about that they're normalized to have length 1, then I need a definition of distance, but that's going to come from the inner product, right? We're going to get the distance squared is the inner product of u with itself. And of course, it's the sine series, which hopefully you've seen before. The square root of 2 is the normalizing term in the norm that I'm gonna, or in the inner product I'm gonna pick. Okay, so this is sine series. Okay, so some of the details, in fact, the main detail, hopefully I've warmed you up on, is what is the inner product? Because I'm going to check out whether this thing really is symmetric using the inner product. Can I take L and take it from one side of the inner product and move it on to the other side, right? And it's also going to tell me, you know, the orthonormality condition will be able to verify that. Okay, so here is the inner product that's going to be used. So I'm going to have the inner product with u and v. So you notice these don't have underbars anymore, so they're not vectors. These are functions of x with x in the interval 0 to 1. And to be able to apply L to them, so to take the second derivatives, then they have to be in this sort of class of things that also has the boundary conditions. So this is working on a set of functions with both of them having the boundary conditions that I want. Right, and the inner product is I take the integral from 0 to 1, u of x times v of x dx. Right, this looks an awful lot like the Euclidean norm of vectors. Oh, someone's phoning me. Okay. You're more important than whatever that phone call is. This looks an awful lot like, you know, ui times vi and sum them up, right? But just in the sort of continuum setting. And if you look at the norm that would come, squared, that's the inner product of u with u, that's the integral from 0 to 1 u squared dx. So this is like the mean squared norm that you may have seen in other contexts. Okay, so I've got this set of eigenfunctions, that's the sine series. There are normalized so that they all have size 1, and they're orthogonal. And you can check by direct computation. And of course, that's probably what you did in a previous class. Oh, there's a question. So there is are U and V given in this context here? That's the question. Or will we be finding them? So now I'm just defining an inner product, right? U is the only thing that we want to find, right? Solving our boundary value problem, the same one we started with last lecture, right? But I'm going to find it in terms of sign series. So I'm going to have a bunch of these things that I'm going to use to build up the solution, right? And this is introduced so I can say it's easy to find the solution in the same way it was easy to find the solution in the linear algebra case because of the orthogonality, right? And if I'm going to talk about orthogonality, then I have to tell you what the inner product is, and there it is. If that's not clear, then follow up with Maricela with a follow-up question or unmute. Okay, now I can say that this thing was orthogonal, verified by direct computation. That's probably what you did the first time you saw the sign series. You multiplied sines functions together, and then you used some Math 101 techniques and showed that they were orthogonal. But because this is a symmetric operator, we don't actually have to do that. We know already that they're going to be orthogonal, and you'll see how that goes. Okay, so symmetry. I'm going to take the inner product of U and L times V, right? And these functions have to satisfy the boundary conditions. Right? So that's the integral from 0 to 1 U V double prime dx, where U and V satisfy the boundary conditions. Now I'm going to say integrate by parts twice. When I integrate by parts once, I'm going to get a boundary term that looks like this. Right? And when I integrate by parts the second time, I'm going to get a boundary term that looks like this. And because of the boundary conditions, those are 0. Okay. So what does integrating by parts do? It takes a derivative from one term and puts it on the other. And you change the sign, but I've done it twice, so the sign doesn't change. I'm going to get U double prime V dx. And this is exactly L times U V, right? And that's what it means to be symmetric, right? In our context is you can start from here and then you can move the thing over onto the other side, right? So symmetric. And notice it's not just the derivative part of the boundary value problem that came into this discussion. It was the boundary conditions as well. So you can lose symmetry either from the interior equations or the boundary conditions. Okay, and then from this, we could work out that the eigen values are real, and the eigen functions are orthogonal. It's the same argument as for the linear algebra case. but let's see it, okay? Right, so I've got L times phi1 is lambda phi1. So phi1 has to satisfy the boundary conditions, right? And I'm going to have a different one with L times phi2 is lambda phi2. Right, these are the sine series. We know that they're orthogonal, but I'm just showing that they are without having to actually do the Math 101 computations. So I can look at this thing, and I know, because L is symmetric, I just showed that I can take the L and put it on the other side. So this is the same as L phi1 phi2. But L times phi2 is just lambda 1, lambda 2, sorry. L times phi2 is just, I just get a multiple. So this is just lambda 2 inner product of phi1 and phi2. This is phi1. I seem to have dropped some subscripts along the way. All right, so L, that's just lambda 1, phi1 times phi2. And if I combine those two things, I get lambda 2 minus lambda 1 times the inner product of phi1 and phi2 is 0. Okay, this is not 0 because I said that I was looking at different eigenvalues. And so this phi1 and phi2 are orthogonal. So we're going to get, in general, we're going to get orthogonal eigenvectors, eigenfunctions coming from this process. Okay, and you've seen sine series solutions before. And I'm just going to say the analog of the eigen solution to A times U is equal to F that we had last lecture is the sine series solution to, I'll say L times U is equal to F. And how does it go? Well, it's a sine series, so you sum up over all of the not all of the eigenvalues now, but all of the eigenfunctions. So these are sine n pi x times the square root of 2. And then you have to divide by the eigenvalues. And the coefficients are the projections of the data onto the eigenvalues, now eigenfunctions. I'm going to write that out a little bit differently. This is an integral that's going to give us a number. So let me put a dummy variable there. So here's the function of x. Here is a coefficient that we found in exactly the same way as before. And there's a 2. Where does the 2 come from? It comes from, where did they go?
It was with the integral
yeah, here we
and
go.
the eigenfunction application.
Right. So then there's the square root of 2 that comes in with the eigenfunction here and also here. So here and here, right? That gives us 2 square roots of 2. And you may have seen the sine series with the coefficients and the inverse series with the 2 all in one place, rather than this presentation where I've got the normalized eigenfunction, so the normalized sine series. but it will give you the same answer in the end, whichever one you do. Okay, and so there's a sine series solution. Let me note this naturally defines a weak solution. F does not have to be continuous to do this. You can look at that. F can be discontinuous. You can find these coefficients still. You can do the sum. It will converge to a function that doesn't have a continuous second derivative, but is nice in every other way, right? So there you go. Okay, so let's look at this idea now of making things symmetric that aren't symmetric. So let's consider now u double prime plus u prime is equal to f. Same boundary conditions. And you can try and see, right? This is, I'm going to call this L times U is equal to F again, different L now. And this is not symmetric. You try and do the same game that we did before, where you look at L times U inner product with V and try and move the L over to the other side. You see that there's a sign change that you can't get rid of, okay? Okay, but we can symmetrize. So if we multiply the equation by e to the x, okay? Well, then I get e to the x u double prime plus e to the x u prime is equal to e to the x times f. And then I notice that this is the same thing as e to the x u prime prime. Right? This is symmetric. Okay. And multiplying the equation by e dx, this is like multiplying multiplying by a diagonal matrix with positive entries. And so if you look at this problem, okay, there's a number in the notes, but okay, I'll just call it star. So that problem now has real eigenvalues. And its eigenfunctions are orthogonal in the weighted inner product and I'm going to give you a concrete example on the first assignment to see how that goes. Okay, we got a natural break because I'm going to talk about Green's functions now, and I am going to give you a poll. The poll is, are complex numbers your friends? Okay, and there's 47 people, so we can see how this goes. Okay, it's been open a minute. There's yeah, a couple people who are not responding, but I'll end and share. Yeah, okay. Everyone's on board with complex arithmetic. Some of the other things I'll say are less well known. I'm not surprised at the inverse Laplace transform. That's a kind of a tricky thing. I would have thought that people with your background would have seen the complex amplitude for harmonic signals. So instead of having you know, a sine representation, sine omega t with a phase, you can have a complex amplitude. But okay, good to know. This is going to come up in some of the examples that we'll look later, and I'll make sure to warm you up on those things. Okay, and I see that a comment that's come up that I just worded it weirdly. Okay, I didn't think it was weird. It was perfectly perfectly worded for me, but okay, that's good to know. Okay, so let's look at Green's functions. And there's going to be a linear algebra warm-up. Exactly like I did with the series solutions, looking at the eigenanalysis of matrices. So here I'm going to have my same system, my n by n matrix, my n component column vector that I'm trying to solve given my n plus n by 1 n component column vector data. So it's a linear system. So something before you learned about eigenanalysis. Was just doing Gaussian elimination on that problem to find the solution. And then after that, it was finding basically the general solution to that process, and that's the matrix inverse. So I'm going to, of course, assume that A is invertible. So I can write U is A inverse times F. And the Green's function is basically the analog of a inverse matrix. And just as a little note, just in case you didn't know this, if A is symmetric, then so is its inverse. So we're going to have a Green's function which will be a function of two variables, but it'll be symmetric in those variables. That's how it's going to come out. Okay, so I don't know if so here's F, here's A inverse. I don't know if this is how you look at matrix multiplication. Okay, I have the picture in my head, and I can't show you like I would like to do, which I normally do. But what do you do to get the first entry of U, first component? You take this row and you turn it sideways, right? rotate it by 90 degrees, and then you take the dot product with f. Right? How do you get the second component of u? Right? You take the second row, you turn it sideways, you take the dot product with f. Right? Again, this would be easier if I used Einstein summation convention, but I guess maybe easier for me, not necessarily easier for everyone else. But the way to look at this is, let's look at it not row by row, but by column, right? The first column of this matrix is always hitting this entry F1, right? So if I looked at F1 as being just 1 and the rest zeros, so if I had a standard basis vector that was 1 with all zeros, right? Then I can see that the first column of A inverse is the solution of A times U is the standard basis vector, right? And of course, then the other columns are the solution of the system with other standard basis vectors. And if you can remember the sort of magical process of finding matrix inverses in your first linear algebra class, it was exactly that, right? You had the linear system, right? Where you had the identity matrix as the right-hand sides. Well, that's like solving the system for all standard unit basis vectors. And then you solved the system and magically the matrix inverse appeared on the other side. That's just this logic. Right, and then of course the jth column is the solution of A times U is, I'll say EJ, the jth standard basis vector. So that's how you find the inverse. But if you look at this, the way to see it is that this inverse is a map from the data to the solution. And it shows exactly how every component of F influences every component of the solution, right? And I can write this matrix multiplication if I do it column by column, right? If I do it column by column, it's F1 times the first column plus F2 times the second column. So I'm going to write that in that way. This is just rewriting the matrix multiplication. I'm going to call the columns of the inverse matrix the vectors G, because it's going to be a Green's function coming up. This is the jth column of A inverse times the data, right? So every data contributes to the solution potentially at every point if all of the entries of these vectors are 0. And that's one way to do it. Okay, so Green's functions are the analog of this idea. Okay, I'm going to go back to my boundary value problem that I started with. It's the easiest one. Well, okay, there's a different easiest one if you don't like boundary conditions. Okay, and I'm just going to tell you, and we'll verify later, that I can get the solution as not the sum over the data, because the sum is a continuous function, but the integral over the data times a Green's function, right? So the G here, really, this is like the matrix inverse, okay, but for in the continuous setting. Okay, and the G that works it's s times x minus 1 if s is less than or equal to x. And it's x times s minus 1 if s is greater than or equal to x. And I'll make a couple of notes. This G is symmetric. Right? And it's another way to define a weak solution. Right? I don't need f to be continuous to make sense of this this integral. Right? If it's discontinuous, I'll just break the integral into two parts, and it's a perfectly fine thing to evaluate the two parts separately. Okay, well, what does this look like? Now, actually, I made a little bit of a mistake in my notes. I should be graphing G as a function of x for given s, but since it's symmetric, it doesn't matter. Okay, so let's look at what did I say? I want to look at it as a function of x. But now I have to tell you I'm looking at it as at a specific value of s. Okay, and it looks like this. So it's 0 at the two ends, okay, like we know it's going to have to be, right? And it's got this thing. And if you're on board with the sort of physics analogy that this thing is describing the linear displacement of a stretched spring, right, with a mass density attached to it, then this thing looks like what you would expect if you had a point mass at that position, right? So this is, look at the response of the system to point masses, and then when you don't have point masses, it's an integral rather than a sum. Okay, so that's the idea here. And there's a whole class on Green's functions. That's Math401. So we're not going to go into much more detail on these things, but it's good to see this. Now, but there's a question that's come up. Why is Green's function considered a kernel? Or am I mistaken? Okay, Green's function, kernel. Okay, yeah, you could use either of those terms to describe this. You can look at other kinds of linear operators that have this form for a general K of X and S. Then it would be a kernel. That's when you're thinking of that as a sort of a forward operator. But we're not thinking of G of X and S as anything. They're specifically calculated to be the solutions of differential equations. And in that context, you would call it a Green's function rather than a kernel. So it's just the direction in which you're going, I would say, is the difference between those two terms. Okay, so I say that that's the solution, and I told you I would verify it later. Let's do that. Let's show that this U, that's this thing here, really is a solution to the boundary value problem. Well, okay. if there's going to be a solution to the boundary value problem, it has to satisfy the boundary conditions. And away from the boundary, it has to satisfy that. So let's check these. So this one, if I look at G at 0 and S, right? If I look at
don't you mean S equals 0 for the Green's function?
No, I want, I'm looking at U of X is going to be G where X is 0, right?
Mm-hmm.
Right? So I want this thing. This is S is bigger than or equal to X, so I'm going to use this form. That's identically equal to 0. And if I look at G at 1 at S, that's when S is less than or equal to X, and so I get that is identically 0. So this is good, right? No matter what the data is, I'm going to get the right boundary conditions. Now let's have a look at this one. Now, to do this, I'm going to separate out the two definitions. And I'm going to take the first derivative and see what comes out. And I'm going to take the second derivative and see if it equals to f of x. Okay. And if I'm going to take the derivative of this thing, is this Math 200 maybe, or an engineering equivalent? But remember, I've got an x on the top, so there's a fundamental theorem of calculus thing that's going to come up. And I've also got x in the integrand, which means I have to take the partial derivative of the integrand as well. So I'm going to get two pieces. Well, from the boundary piece, I'm going to get this thing evaluated at x. Okay, I think I've got a mistake in my notes. I think this should be x times x minus 1 f of x. And then I'm going to get the integral from 0 to x of the derivative of that thing. That's just s times f of s ds. Okay, in this one, I'm going to get the fundamental theorem of calculus, but with a negative sign. And that'll be x times x minus 1 f of x. That's the value of the integrand at the lower limit of this thing. And then I'm going to get plus the integral from x to 1 s minus 1 f of s ds. And you'll notice these things cancel out. Now I'm going to take the second derivative. Right? And okay, well, now there's no x in the integrand anymore. This is a particularly simple case, right? So I'm just going to get the fundamental theorem of calculus. I'm going to get x times f of x. And then I get minus x minus 1 f of x coming from the derivative at that lower limit. And you notice if you put those together, magically, you get f of x. Okay, so by my watch, is it stopped? Oh, okay. By my watch, I have 3 minutes. By the clock, I have 1 minute. I'm gonna keep going a little bit because I want to end by comparing what comes out from the series solutions and the Green's function solution. Okay, let's look at the series solution. I had u of x is And from the Green's function, of course, these are the same solutions, just two different representations of the solution. Okay, so let's compare and contrast. The way to think about it is that this is like a kind of global result, right? It says, hey, there's different components of the right-hand side, and this is how they impact the solution. And I think one of the important things to notice is this denominator. Clearly, this shows that large n components of F are highly damped. If n is 10, like you're dividing by 900, right? So that component is not going to be very important in the resulting solution, right? So this is kind of a nice thing to look at when you're trying to isolate basically the dominant behavior in what you're looking at. And okay, this is like an exact list of what is important most to least. And so certainly you could get a lot of insight into how this is behaving with a single component or just a few components, right? What do we like about this one? This one does not give you that, right? But it's more of a local result. And it's the exact map of data to solution. Can tell exactly what would happen is if you change the data locally at one point, how that's going to affect the solution globally. And so that's pretty good. So there's no winner here, right? There's no one who's clearly better than the other. They are things that give you different types of information about the solution. And these are the sort of two main techniques that we're going to have coming up for the other problems that we're going to look at in the next few weeks. I can say next week, at least Tuesday's lecture, we're going to take a step sideways and look at some modeling, scaling and non-dimensionalization, linearization that actually leads to this boundary value problem that we've come to know and love. And why that's important is, okay, to know where these things come from. Okay, that's just interesting. But if you wanted to extend these type of models to sort of more general behavior, you actually have to know a little bit about the behavior and how that enters. We're going to have some interesting problems with variable or discontinuous coefficients. And depending on the model they come from, different mathematics comes out. And so this is something you'll see in that discussion. Okay, I'm going to end there. I went over my thing where I said I would end at 10:45, but at least you've got 10 minutes. But like last time, I'm going to stay on for, I'll say as long as you want me, or an hour. But everyone that needs to leave can leave at this point. I'm going to stop recording and happy to answer any questions that come at the end of the class.